Hello and welcome to another exciting calculus video. We've just finished chapter 2, how to derive. So we're going to look at the start of chapter 3 here, applications of differentiation. Once you know how to derive, what can you do with the things? So here's an overview of the chapter. 3.1 we're going to start today, extrema on an interval. Next section, Rolle's theorem and mean value theorem, the MVT. Section 3.3, increasing and decreasing functions and the first derivative test. 3.4, concavity and the second derivative test. And then 3.5, we do some curve sketching. All these little calculus tricks will make our graphs even better. 3.6, a very good applied section, optimization problems. And then 3.7 is a little wrap-up section called differentials. Now the first four, I'm just going to sum up in one picture. So here, chapter 3, applications of derivatives, the big idea. So here I've just drawn a curve cutting through the xy axes, and I wrote, what are the interesting parts of any graph, and how would we locate those interesting features? Well, one of the easiest, and you've been doing this even before calculus, we can find, I used blue dots here, we can find the x-intercepts. And how do you find the x-intercepts of an equation? You just set the function equal to 0, because the x-axis is height 0 on the y-axis. So if you set your function equal to 0, you'll find the x-intercepts. Okay, what's next? Notice I put the red dots here on the peaks and in the valleys, the highs and the lows. Those are minimum and maximum values. How do you find them? Well, at those points, the tangent line would be horizontal. Tangent lines have slope 0 if they're horizontal. So to find the mins and maxes, you set the derivative equal to 0. Okay, now a little more subtle. In between the peaks and the valleys, like let me go here, I can get blue ink. Here's a peak and here's a valley. Somewhere in between the peak and the valley is going to be what's called a point of inflection. How would we find that? We're going to set the second derivative equal to 0. And there's another one over here. You know, we've got this peak, this valley. Somewhere in between a peak and a valley, there should be a point of inflection. And that is going to cover, I think, the first 4 sections of the book. Yeah, 1, 2, 3, and 4 here are all summed up in the picture. Function equal to 0 are x-intercepts. Derivative equal to 0 are the mins and the maxes. And the second derivative equal to 0 will point us toward the points of inflection. Here's the assignment for this section, 217. We got some problems from the book and 3 on WebAssign. And let's get the party started. Finding extrema. Extrema are just the extreme values, the minimums and the maximums. And it says we're going to understand the definition of extrema of a function on an interval. We will understand the definition of relative extrema of a function on an open interval. And we will find extrema on a closed interval. And the book says, in calculus, much effort is devoted to determining the behavior of function f on some interval I. Does our function have a maximum value? Does it have a minimum value? Where is the function increasing? Where is the function decreasing? In this chapter, we're going to learn how derivatives can be used to answer these questions. You'll also see why these questions are important in real-life applications. Now here, one of our confusing math definitions. Let f be defined on an interval containing I, and that interval contains point C. F of c is a minimum of f on the interval when f of c is less than or equal to f of x for all x's in the interval. F of c is a maximum of f on I, that interval, when f of c is greater than or equal to f of x for all x's in the interval. The minimum and max of the function on an extrema are the extreme values, or the extrema. The singular form of extrema is extremum. of the function on that interval. The min and max functions on an interval are also called the absolute min and the absolute max, or the global min and max for the interval. So let's clear up a little bit of stuff here. First, let's look at this definition. It is very wordy and very confusing. Let me draw an x and y axis. So here we've got c, and we've got some output f of c. Let's look at the first one. F of c is a min. So if I plot that point in there, put it right here, c and f of c. It says that point is a min when f of c is less than or equal to all other f of x's. So if I pick any other x value here on the x-axis and map it to the y-axis, f of c is going to be less than all of them. So I'd start plotting these points, and they're all going to be higher. Oops, get up there. So any other point is going to be up higher than f of c. So we can see by the graph, yeah, that is a minimum. It's at the bottom of a valley. And let's see, that point f of c is a maximum if f of c is greater than all other outputs in its neighborhood. So if I plug in these other outputs, maybe they're coming in down here like this, that means that the c value leads us to a maximum, the top of a hill. Now here, when they talk about extreme values, and especially the globals or the absolute mins and maxes, let's say here's my interval, goes from here to here, and my function looks like this. Any hilltop is a local max. So this would be a max, this would be a max, this would be a max, as well as this one. They're all local maxes. They're the highest peak in the neighborhood. But if we look at all four of these, the highest of all the peaks, this would be your global or your absolute max. You know, these other maxes they're king of their own little hills, but out of all the hills, this is the king of them all. So that would be our global or endpoint, or our global or absolute max. Also notice here it says extrema can occur on the interior points or at the end points. Let's say again we have an interval like this, and let's say we have a little peak here, but then it goes up like this. You might think this is the maximum value on the interval, but if we check our endpoint, our max might be way up here. So when we're doing these checks, don't forget to check your endpoints. The min or the max may occur at an endpoint. Okay, let me make these a little bigger. It says here, a function need not have a min or a max on an interval. For instance, in the figures we're going to see down below, x squared plus 1 has a min and a max on a closed interval, but does not have a max on the open interval. Again, we'll look at these here. It's better to see in the picture. Okay. So we're looking at this. We've got a parabola x squared plus 1. Our interval is -1 to 2. So just by looking at the graph, here's as low as the graph goes. That is our minimum on the interval. And the highest our graph goes, here it occurs at an endpoint. So our max is on this right endpoint at x equals 2. And it says down here below, f is continuous. Our function is unbroken the entire time we drew it, and our interval, -1 to 2, is closed. Notice here we have the brackets on the ends, and if we have the brackets, that means our function will have closed dots. So this is our max because it is part of our function right at the end of the interval. So, oops. Okay, let's slide this over here. Now notice what's changed. F is still a continuous function, but now our interval is not closed. Our interval's open, so we have these open parentheses here on the end. So when we look at the graph with these parentheses at -1 and 2, we now have open circles at the edges of our graphs. So here we can still see we have a minimum. Our minimum is the bottom of the valley. So we still have a min value, but do we have a max? Over here, our endpoint was closed. So we could approach and actually attain that point. So that point was our maximum. Notice here now it's an open circle. We can never attain that endpoint. So if we're looking for the max, how close can we get to that point without actually getting there? Well, we can get infinitely infinitely close. There's actually one more step always to take. Since there's always one more step to take, we're never going to get there. That cannot be a max because our interval is open and not closed. The last scenario, notice now our function is, we're back to a closed interval, but our function is no longer continuous. If we look at the graph, we actually have a hole right there at the bottom of our parabola. So if we look at the max, we do have a maximum again. Because this point is plugged in, we have our max, it's equal to 5. But down here, do we have a minimum? We're going to approach the hole in the graph. Are we ever going to get there? No, because we can approach it and get infinitely close without ever getting there. So because our function is not continuous, we no longer have a minimum value. We only have a max now in this case. So this leads us to the extreme value theorem. And what we just did here was a setup. Notice we had two things below. Our function being continuous. Was the function continuous? And was our interval open or closed? So here in the theorem, it's pretty straightforward. If your function is continuous and your interval's closed, then the function is guaranteed to have both a minimum and a max. So to sum it up, if your function is continuous and your interval is closed, if your function's continuous and it's closed, then you are guaranteed both a minimum and a max. Then you're going to have a max and a min. It is guaranteed by the extreme value theorem. But again, you got to have the if part satisfied. If you're continuous and your interval's closed, then you're guaranteed a min and a max. And do I have that figure? Oops. Yes, I do have that figure. It says figure 3.2. That is right here. I'll just move it over to this slide. Oops, get. There we go. There we go. In the figure, the graph of x cubed minus 3x squared has a relative max at the origin, 0, 0. If we look at that, there is a hill, and the top of the hill is right at the origin. And it has a relative min at 2, negative 4. So here at 2, negative 4, we're in a valley. The points right around it are higher than it, so that is the lowest point. That is our min. Informally, for a continuous function, we can think of the relative max as occurring on a hill and a relative min as occurring in a valley. Such hill and valley can occur in two ways. When the hill or valley is smooth and rounded, the graph has a horizontal tangent line at that high or low point. When the hill or valley is a sharp or peaked, the graph represents a function that is non-differentiable at that point. So here, our definition box, what is a relative extrema? If there's an open interval containing C, on which f of C is a max, then f of C is called a relative max of our function, or we can say that f has a relative maximum at that point. If there's an open interval containing C on which f of C is a minimum, then f of C is called the relative min of the function, or we can say that f has a relative minimum at that point. The plural of relative maximum is relative maxima, and the plural of relative minimum is relative minima. Relative maximum and minimum are sometimes called the locals, the local max or the local min, as opposed to the global. Remember, the global max would be the highest of all the hills. You can have several local maxes, but only one global. And finally, we get to do an actual example. Well, kind of here. I guess we are going to do a little deriving in this one. Here, example 1 examines the derivatives of function at a given extrema. So I think the first few out of the book or the web assign are going to be very similar. They're going to give you a point and tell you that it is definitely an extrema. More is said about finding them in a later section. So here, Find the value of the derivative at the extrema point shown. So here in graph A, we've got our function. I'm not going to read through it. You can see it right there. And they give us the point of a max. And they want us to find the value of the derivative at that point. So what we want is f prime 3. So that's our point 3 comma 2. We should take our derivative and plug the 3 into it. So it looks like we're going to have to do a little quotient rule. Let me move this over here. And I'm going to mentally distribute the 9. So that's going to be, I'll just write it in there, 9x squared squared minus 27. I'm just going to rewrite it down here. 9x squared. Actually, I'm just going to start a new slide. 9x squared minus 27. And then our denominator is x cubed. So we're going to do a little quotient rule. What's our d high? 18x. What's our d low? 3x squared. So our derivative, f prime, remember the quotient rule starts with low d high, so here's our low, x cubed, and we're going to multiply that by 18x. So there's low d high minus high d low. So we're going to multiply on this diagonal, and since this is more than one term, I'm going to group it in a set of parentheses. So our d low is 3x squared. Our high is 9x squared minus 27. And don't forget our denominator for the quotient rule, low times low, or that'll be x cubed times itself, or x to the 6. Okay, the calculus is over. Now it's just a bunch of algebra and simplification. So let's see here. We multiply these. We're going to have an 18x to the 4th. Minus, if we multiply here, distribute, that is going to be minus 27x to the 4th. And then a plus negative 3, negative 27. That's a plus 81x squared. All over x to the 6. And we can combine some like terms in the numerator. 18 minus 27, that's negative 9x to the 4th plus 81x squared over x to the 6. Okay. We cannot reduce our coefficients, but notice everything has a power of x, and the lowest of those is x squared. So we can go through this and knock all our x's down by 2 powers. So this will become x to the 0, which is just 1, so that's a plus 81. And if we reduce this power by 2, that's a negative 9x squared. And then our denominator power is going to drop also by 2, x to the 4th. So there's our derivative. Now if I click back one slide, remember we were trying to find f prime at 3. So f prime at 3, we're going to plug in a 3 for this x. And when we square 3, that's going to become a 9. 9 times the negative 9 is negative 81 plus 81 over, downstairs would be 3 to the 4th. Now all the important stuff is happening in the numerator. If we add up our terms in the numerator, we get 0 divided by 81, and 0 divided by anything is 0. Is that answer correct? Well, remember, and when we set this up, they assured us that this was a relative max. So if we drew a tangent line there, what would it be? Well, it would be horizontal. And what is the slope of our horizontal line? The slope is 0. And that's exactly what we verified here. If we had not gotten a 0, we would have figured out we had made a mistake. All right, let's see what letter B looks like. Get that out of here. We don't need this anymore. At x equals 0, what is the derivative of absolute value of x? Make that look a little better. There we go. Okay, now think back to when we were first doing derivatives. If we look at this one here, on the left side, the derivative from left. So as we approach 0 from the left, what is the slope of this red line? Well, that slope equals -1. What about the derivative from the right? So over here, the blue part, well, that slope is +1. +1. So remember, if the derivative from the left and the derivative from the right are not the same, then that derivative does not exist. Derivative dne. Okay, let's move on to part C. Let's get down the graph here. So now again, they gave us some points that we know are mins and maxes. So here we've got a point, half pi comma 1 is a max, 3/2 pi comma -1 is a min. There's the good old sine wave back from pre-calc. And they want us to verify those or find the outputs. So here f of x is sine, so we're going to derive that. F prime, derivative of sine is cos of the same x. All right, I'm going to stick with the blue ink. Let's check out this first point, pi over 2 comma 1. So what is f prime at pi over 2? That would be the cosine value at pi over 2. And remember, if you think just about the coordinate axes, pi over 2 is up here. That point would be 0 comma 1. So the cosine value is your x coordinate. So the cosine at a half pi is 0. And we would expect a 0 because that tangent line should be horizontal. And if we sneak down to the valley, f prime at 3 pi over 2, that's going to be the cos at 3 pi over 2. And that moves us down to this point, 0 comma -1. But still, we're plugging in the x-coordinate, or our x-coordinate is our cosine value. So this one is also equal to 0. And we would also expect a horizontal tangent line there touching the bottom of that valley. All right. Note in that last example that at each relative extremum, the derivative was 0 or it did not exist. The x value at these special points are called critical numbers. I think in pre-calc we might have called them key numbers when we were solving inequalities, but here they are critical numbers. So find where your derivative is 0 or non-existent. Figure 3.4 down here illustrates two types of critical numbers. Notice in the definition that the critical number c has to be in the domain of f, but c does not have to necessarily be in the domain of the derivative. So definition of a critical number, let f be defined at point c. If the derivative is equal to 0, or if f is non-differentiable at that point, then that point is a critical number. And here graphically it's easy to see what's going on. Either over here you're going to have a spot where a horizontal tangent line would touch. That's a nice smooth peak or valley. If you have a sharp cusp, it's no tangent line is going to work there. The derivative does not exist. Those both will lead you to key numbers or critical numbers. Yeah, on the AP exam, the wording they might call them critical values as opposed to critical numbers. Tomato, tomato, potato, potato, they're critical. They're important. Now, our theorem. Relative extrema occur only at the critical numbers, or maybe at the endpoints. If f has a relative min or max at a x value, then that x value is a critical number of our function. Oops, get out of there. That is a critical number of our function. So how do we find these extrema on our interval if it's closed? And it says Theorem 3.2 states that the relative extrema of a function occur only at the critical numbers. Knowing this, we can use the guidelines to find them on a closed interval. Okay, so step 1, find the critical numbers. Set your derivative equal to 0 or find where the derivative fails to exist. 2, evaluate the original function at these critical numbers. 3, evaluate the endpoints. Sometimes the min or maxes can occur at the endpoints. Number 4, the least of those values is your min. The highest of the values is the max. And the next 3 examples are going to show how to apply these guidelines. Be sure you see that finding the critical numbers of a function is only one part of the procedure. Evaluating the function at those critical numbers and at the endpoints is the other part. Insight. When the AP exam asks for an absolute extremum of a function on a closed interval, be sure to evaluate those endpoints. The mins and maxes can occur at endpoints. It's very easy to forget to check those endpoints. Okay, example 2. I believe this is a nice, very straightforward way to figure these out. Find these extrema on a closed interval. So here, find the extrema of this function on this interval. So if I skip back to here, first we're going to find the critical numbers. We need our derivative f prime, so we can set it equal to 0 or find where it does not exist. As I derive that, little power rule is going to give me 12x cubed minus 12x squared. Okay, so there's our derivative. Let's set it equal to 0. And to solve, we're going to factor out a 12x squared. So that'll leave us an x from the first term and a -1, a placeholder for the second term. And if we set that equal to 0, we can set our first piece equal to 0 and get x is 0. And if we set the parenthesis equal to 0, we'll get x is 1. So here are the critical numbers, 0 and 1. So if I go back here, we found the critical numbers. Now we're going to evaluate the critical numbers in the original function, and let's combine it with 3 at the same point. We're also going to check the endpoints of our function. So let me do it like this. There we go. So the critical numbers we found were 0 and negative, was that 0 and 1. So we're going to do f of 0 and see what comes out of the function. And we're going to do f of 1 and see what comes out of the function. But we're also going to check the endpoints. I'll switch to blue ink. We're going to find f of -1. And we're also going to find f of 2. I like that with the different color ink. The critical numbers come in the inside of the interval. The endpoint numbers can also be mins and maxes, so we're going to also check those. And again, we're always going back to our original function. So let me get this out of here. All right. So if we plug -1 into the function and evaluate it, out pops a +7. If we put 0 into the original function, out comes a 0. If we put a 1 in there, we're going to get 3 minus 4. That's -1. And if we put a 2 in there, out pops a 16. So here we are. We evaluated the endpoints and the critical numbers. So we pick our high and our low for the min and the max. So the lowest of all these numbers is -1. So 1, -1 is our min. And then if I look at all those numbers and pick the biggest, it's 16. 2, 16 is the max. So we found our min and our max in the closed interval. And notice we did have a max on an endpoint. If you forgot to check your endpoints, you might have thought 0 was the max because it's the highest number out of the criticals. And let me see here. We got a graphical solution. So here's what the graph of this looks like, and they put a pink box around the interval. So here, -1, we have a bracket there, and at 2, there's a bracket. So here's our interval, and we set our derivative equal to 0 to find these points, 0 and 1. So they would both have horizontal tangent lines there, and we evaluated one, and we had an output of 7. That was pretty high up there. But when we checked the other endpoint, we had our max of 16. So that was our global max. It's the max of the entire interval. It's the highest point on the interval. And then if we look for the lowest point on the whole interval, well, that was our 1 comma negative 1 that we found right here. 1 comma negative 1 was our minimum. Okay, yeah, and there's what it would look like on a graphing utility. Ooh, now let me point this out too. In the figures, note that the critical number 0 does not yield a min or a max. This tells you that the converse of the theorem is not true. In other words, the critical numbers do not produce relative extrema. Let's go back and review that there. So it says here, oops. If we have a min or a max, then that is a critical number. The converse is not true. Just because it's a critical number does not mean it's going to be a min or a max. Okay, here I think this was a warm-up from years past. If the function f is blank on a blank, then you are guaranteed both a blank and a blank. Well, if your function is continuous on a closed interval, then you are guaranteed both a min and a max. You're going to have one of each. As long as you're continuous, as long as your interval's closed, you are guaranteed one of each. So here, example 3. Find the extrema f of x is 2x minus 3x to the 2/3 power on this given interval. All right, step 1, find the critical numbers. And that means we got to derive f prime. Well, derivative of 2x, that's just going to be a 2. And then we're going to have minus. Here we're going to bring down that 2/3, multiply by the 3, so that's 6/3. 6/3 is 2x to 1 power lower, to the negative 1/3. Okay, now we need to do a little algebra work before we can find our critical numbers, because we want to set this equal to 0, and that's not going to be very helpful unless we turn it into one fraction. So here we've got 2 over 1 minus 2 over, and let me see, should I put this back under a radical? Yeah, let's do it as the 3rd root of x down here, 3rd root of x. So we want to set this equal to 0, and that's not much help now unless we can get this down to be one fraction. And we're not far. Our common denominator is 3rd root of x, so we're going to multiply this side by the 3rd root of x. That means our numerator also gets multiplied by a 3rd root of x. And then I'm just going to sort of sneak over this way. Our denominator is just the cube root of x. And then up here, we're going to have 2 cube root of x minus 2. Let's factor the 2 out. So now it's just cube root x. That's a cube root. That's a 3. And then a minus 1. We've just factored this 2 out. So there's our derivative. And since it's in the form of a fraction, this is f prime, we're going to set the numerator equal to 0 and find out the x value from the numerator. That'll give us one of our key numbers. So if we set that equal to 0, the first thing I'm going to do is divide a 2 out. So what we're left with is the cube root of x minus 1 equals 0. So let's add 1. Now the 1 is on the other side and it's positive. And to get rid of the 3rd root, we're going to 3rd power. So if we cube the left, we get x. If we cube 1, we get 1. So here's our critical number from the numerator, set it equal to 0. And then downstairs, this one's even easier. If we set that equal to 0 and we cube both sides, we get x is 0. So notice this one is where our derivative equals 0. F prime is equal to 0. So this would lead to a horizontal tangent line, but this one is where our denominator equals 0. That's where the derivative does not exist. So we've got 2 critical numbers, and we've also got our end points. So we are going to check these out. We're going to do f of -1. That's one of our endpoints. We're also going to check f of +3. That's our other endpoint. And then we have two interior critical numbers. We're going to check out f of 0 and also f of +1. Now, to evaluate these, I don't like fractional exponents. We're going to do 2x minus 3, and then that is going to be the cube root of x squared. So if we plug in the -1, that's going to become a -2. We'll square the -1, that's a 1. The cube root of that is 1, times 3 is just a -3. So if we do -2 minus 3 more, we get -5. 0 is easy. Plug in a 0. 2 times 0 is 0. Minus that mess is going to turn into a 0. 0 minus 0 is 0. Let's plug a 1 in. 2 times 1 is 2. This squared will be a 1. The cube root of 1 is 1. Times 3 is 3. 2 minus 3 is -1. And finally, 3 goes in there. It's not going to come out nice. It's going to be a decimal because we're going to have a root in it. But if you type that in a calculator, you're going to get approximately -0.24, -0.24. So we have evaluated our crit numbers and our endpoints. Let's find the min and the max. As I scan those, bunch of negatives. The deepest negative is this one. So we have a minimum at -1, -5. Out of all of these, the biggest is 0 because everything else is negative. So we have a max at the origin. Okay. Let's see what that looks like as a graph. Oop, I maybe shouldn't erase that there. So here's what the function looks like. And it's real neat to see. Of course, we can see the non-existent point. Remember, this point came from our denominator eating 0. It's non-differentiable. So we cannot have a tangent line at that sharp cusp. But it did also turn out to be our max. If you look, it's the highest point on the graph. Our min was when we entered the interval. Our left endpoint, -1, gave us our output -5, so that's the lowest this graph goes on the entire interval, shaded in pink. Okay, good stuff. Example 4, we're not having fun unless we throw some trig functions in there. We got some sines and cosines, and I just noticed, I think this is our last example. Yeah, so here we go. Find the extrema of this. 2 sine x minus cos 2x. Our interval is 1 trip around the unit circle, 0 to 2 pi, and they do, since they gave us the graph, we can see where the horizontal tangent lines looks like they're going to fall. So it looks like we got a global max here. We might have a couple min here, another max there. Let's not get distracted by the graph. Let's do some sweet calculus. So here's f of x. Let's derive it. F prime. Oop, I'm going to switch to black ink. So derive f, we get f prime. First term's nice and easy. It's just straight up derivative of 2 sine. Well, derivative of sine is going to be cos, and 2 is our constant multiple, so it comes along. And now here, this is going to be a little chain rule. We're going to derive cos, so that's going to become a negative sign. So that's going to hit this minus and change it to a plus sine 2x. But remember, this is going to use a chain rule, and the derivative of the inner function 2x is going to be a 2. That's why I left that little gap there. 2 sine 2x. Okay, so we've got a derivative. And our next step is going to be to set that equal to 0, but we're going to kind of get stuck because we usually have something we can factor and set the factors equal to 0. So we're going to have to dig back into our pre-calc memories. This first term I'll leave in black ink. That's not going to change. That's just 2 cos of x. But I'm going to switch to red ink. The sine of 2x. There's an old pre-calc formula, double angle formula. The sine of the double angle 2x is the same as 2 sine x cos x. So I sort of mentally just imagine that 2 jumps out front. So you're going to have a 2 sine x, and then sine is lonely, so cos comes to join it. We're going to make this substitution in our problem. So this 2 sine of 2x is out. Now, since there's already a 2 here, that's going to get hit by this 2, and that's going to become a 4 sine x cos x. That's supposed to be an s x equal to 0. Okay, now that it's equal to 0, now we can actually factor something. Notice we've got a cos and a cos, we've got a 4 and a 2, so we're going to factor out on a full 2 cos x. So let's see what's left inside. I'll switch to blue ink. This got factored out in its entirety, so there's a 1 left to hold its place. Plus, we factored a 2 out of the 4, so there's still a 2 there. And this cos x got pulled out entirely, so that just leaves the sine x there. And that's equal to 0. Okay, now we can set our factors separately equal to 0. So this one, where does 2 cos x equal 0? Well, we can divide by 2, so the 2 just disappears. 0 divided by 2 is still 0. Now think on the unit circle. Where is cosine equal to 0? Cosines are our x values, so that would be here and here. Top and the bottom of the circle, that's half pi and 3/2 pi. X equals half pi and 3/2 pi. All right. This next term, I'll switch back to blue. If we set that equal to 0, the first thing we're going to do to get sine x alone is subtract 1. So over here it's a -1. And then to get the sine alone, we're going to divide by 2. So sine of x, -1/2. Break out your unit circle, and you'll find that those x values are 7 pi over 6 and 11 pi over 6. So now we've got 4 critical numbers, 1, 2, 3, 4, and we have our endpoints that also need checked. So I believe in the notes there's sort of like a little box that goes with, I'm going to just do it the way I did before with the function notation. We're going to do f of our left endpoint, 0, see what that is, and then we're going to do f of I guess our smallest one is pi over 2. And then we're going to do f of 7 pi over 6. And then f of 3 pi over 2. F of 11 pi over 6. And then our right endpoint, f of, I should switch back to black ink to stay consistent, f of 2 pi radians equals. All right, now a good amount of these you can just do with your unit circle, or you can plug them into a calculator. So let's do here, f of 0, plug 0 into here, out pops a -1. If we put in the pi over 2, again, we're just going back here, so that'd be the sine at pi over 2 times 2. When we plug the pi over 2 in here, you're going to double it, so that would be the cos at pi. When it's all done, it turns out to be a +3. For the 7 pi over 6, we plug that in. That's -3/2 or -1.5. If we put in the 3 pi over 2, out pops a -1. At the 11 pi over 6, our output is -3/2, -1.5. And then finally, at the right endpoint, we plug that in, and out comes a -1. So let's look for our highs and our lows. The biggest number is our only positive number. So we have a max at the point half pi comma 3. Now when we go for a min, it looks like we have a tie. -1.5, -1.5. So we do have a tie. We have 2 minimums. The minimums are at 7 pi over 6, comma -3/2, and also at 11 pi over 6, comma -3/2. It's a tie. Okay, I think we answered this one fully. Find the extrema, we derived, we found our interior critical numbers, we checked our endpoints, and this is a good one. You know, if we had forgotten to check our endpoints, it wouldn't have harmed the problem at all. We would have still found the right mins and maxes, even though the endpoints were not checked. And again, if we go back and look at our graph, it's going to verify what we just found there. Here at pi over 2, that was our max. We also had a max here, but that was not, well, no, it was not our global max. We're just looking for the highest of the highs. We did have a local here, but what we're finding are only the extreme values on the entire interval. But our tie for the min, I'll highlight that in red, at 7 pi over 6 and 11 pi over 6, the tangent line there would be the same for both. So that is our min is at that low spot. Up here, the tangent line would be at our max. Okay, and there's a good intro to 3.1, Extrema on an interval. Take a look at the WebAssign, and when next time I see you in class, we're going to do some of these odd problems. I'm looking forward to it. See you.